Hello, and welcome to Chapter 2, Chemical Basis of Life. This chapter is really just an overview of atomic structure and a few molecular structures and some bonding, so we'll get through this pretty quickly. Most of you have already taken some chemistry, so you have a general idea of what all of this is about. So we know that atoms, of course, are the smallest functional units of all matter. And atoms themselves are actually made up of subatomic particles. But when we talk about an intact structure, we would be looking at the smallest unit of matter being an atom. Atoms cannot be further broken down other than into individual subatomic particles. Every type of atom is specific. So we have carbon atoms, hydrogen atoms, helium atoms. They are all based, they all make up each individual specific type of atom is what makes up our chemical elements or our periodic table. In atomic structure, we have the three subatomic particles: protons, neutrons, electrons. Protons have a positive charge, neutrons have pretty much a neutral charge. Both protons and neutrons are found together to form what is referred to as the nucleus or the center of an atom. Surrounding that nucleus are electrons. Electrons are negatively charged. They're extremely small, and they are found in these cloud-like regions surrounding the nucleus of the atom called orbitals. And we're going to talk real quick about an orbital and energy shells because that plays a role in how atoms are attracted to each other. When an atom is in its entirety, it has all of the appropriate neutrons, electrons, and protons. The number of electrons and protons are equal. So technically, or we should not say technically, but generally, an intact atom has actually no net electric charge. Since electrons are negative and protons are positive, they will cancel each other out since their charge is essentially equal. So these electrons occupy these areas surrounding the nucleus of an atom, the protons and neutrons, called orbitals. And sometimes orbitals are looked at like kind of this little soul, like the entire atomic structure, I should say, is kind of seen as this little solar system, as if there's a sun with all of these planets rotating around it. And that's the general idea, but really it's a little more complex than that. Electrons travel within not just an orbit, but they actually are in this cloud-like structure. And that area is, when we define an orbital, it's just really defined as an area in which an electron may be found. It's more accurately depicted, again, as a cloud as opposed to an actual orbit or pathway. So here we have your typical hydrogen atom on the left and a helium atom on the right. And you can see the hydrogen atom has one proton, one electron. We don't have a neutron here in the hydrogen atom. But as we move up in atomic number, so we're moving up to helium. Helium is the second element. It's a noble gas found on the periodic table. And helium has two protons, two neutrons, two electrons, and this picture is just depicting those subatomic particles and where they would be found in a typical atom. So we have different types of orbitals. There are s orbitals and p orbitals. That's all that we're going to be looking at in this course. In your general chemistry and organic chemistry classes, you may move up into d orbitals and hierarchies further out. We're just going to look at s and p orbitals, and we're only going to look at two energy shells. So an s orbital is spherical, which is why it's called an s orbital, and p orbitals have a propeller or dumbbell-like shape. You can see in the bottom right here is our s orbital. It's nice and circular, and then we have our p orbital here, which is kind of dumbbell shaped. Each orbital individually can only hold two electrons. So any atom that has more than two electrons, so anything on the periodic table beyond helium, is going to have more than one orbital. Now the s orbitals, there's only two of them. We have a 1s and a 2s. You can see those are depicted here. And then we move into the p orbitals, and the p orbital is a little more complex, a little more three-dimensional, so to speak. So let's move on into these orbitals. As we progress throughout the periodic table, atoms are going to have more orbitals, and these orbitals are going to fall into even larger, more broad type classifications known as electron shells. And these electron shells are just basically kind of like measurements. As we get further away from the nucleus of the atom, these energy shells contain orbitals. Now, the very first orbital or the very first energy shell only holds the 1s orbital. So the first energy shell is the first orbital, and there are only 2 electrons available in the first shell. The second energy shell, which is the last one that we're going to look at, contains the 2s orbital, which is a spherical, so there's 2 electrons, and then 3 of the 2p orbitals. So it holds 2px, 2pz, and 2py. And those 3 dumbbell-shaped orbitals give us a total of 3 more pairs of electrons. So ultimately, the second energy shell, holds 2 electrons from 1s and 6 electrons from the 2p orbitals, and that's a total of 8 electrons, or 4 pairs. And electrons, with the exception of hydrogen, usually occur in pairs. So orbitals are basically the path, or that cloud, and then the shells are where these clouds are kind of brought together. Think of them as compartments in which these orbitals will be held. So it's just a hierarchy of organization in the atom. So the number of electrons is just a table from your book that kind of gives you a general idea. In the 1s, or the first energy shell with the 1s orbital, we have 2. It's spherical. And then in the second energy shell, we have both the 2s and 2p, total of 8. Now, those 8, when we get into the second shell and higher, there's a concept known as the octet rule. And this octet rule is that there are a total or maximum of 8 electrons per energy shell. So let's take a look at nitrogen, because nitrogen is an element that can form 3 bonds, and it can do so because it has 3 electrons that are unpaired. So how does this element fill these energy shells in orbitals? Well, it has 7 protons and 7 electrons. So the very first, the 1s, gets filled with its first electron, and then that electron gets its pair, and the 1s orbital will be full with 2. So that leaves us with 5 electrons left. The 2s orbital, which is also a spherical orbital, will fill with the third electron and then the fourth. So the 1s and 2s orbitals will be full. First energy shell is full. The second energy shell is being filled. And it right now only has 2. That leaves us with 3 electrons. Now remember, the p orbitals are dumbbell shaped. They have that kind of, each orbital looks kind of like this, like a figure 8. And normally we would pair 1 electron here and 1 electron down here. But these orbitals each get filled with 1 electron before going back and filling it with the other electron. So we're going to get rid of this one here. And so we get an electron on this p orbital, an electron on this one, and an electron on this one. This will give us our last 3 electrons for a total of 7. Now, since these p orbitals are not completely filled, they now have the ability, they want another electron. They want a pair. Electrons want to occur in pairs in these orbitals. So since these orbitals are only half full, this means that nitrogen has the ability to share up to 3 electrons with another element. Now, in atmospheric nitrogen, that would be another nitrogen atom. So atmospheric nitrogen, N2, N2, atmospheric nitrogen is just 2 nitrogen atoms sharing each of their single-filled orbitals here, so that their orbitals each, at least some of the time, will have 2 electrons. So this allows nitrogen to share up to 3 electrons with another element, or form 3 different covalent bonds. And covalent bonds are the sharing of electrons. So here's the structure. Here's our nucleus with our 7 protons and neutrons. And then we have our 2 electrons in 1s, right? So that's our 1s. And then here's our second spherical shell. So here's our 2s. We're moving into that second energy shell. And then here's the single electrons in each of those p orbitals, so that these guys are going to want to share with something else. That gives us a total of 7 electrons, which is what nitrogen has. Here's just another three-dimensional type depiction. It's important to remember these p orbitals have three planes. They have an x plane, a y plane, and then a z plane, kind of like coming out at you as if it were in 3 dimensions. And here is your kind of nomenclature for the energy shells and orbitals. You always depict the shell number and then in brackets those orbitals that are part of that particular shell. So how many protons are actually in the nucleus of an atom is referred to as its atomic number. So hydrogen has an atomic number of 1, it has 1 proton. Nitrogen has an atomic number of 7, it's number 7 on the periodic table, it has 7 protons. And the number of protons is also equal to the number of electrons. That's what gives an atom that no net charge, that zero charge or neutral. So the number of protons equals the number of electrons. But just remember that the atomic number itself is actually based on the protons, and then the number of protons equals electrons. And that is in an electrically neutral atom. Now the periodic table is organized by the number of protons. The rows, each individual row corresponds to how many electron shells those atoms have. The columns from left to right indicate how many electrons are in that actual outer shell. So remember, we have the inner energy shell 1 and then energy shell 2. As we move down through the periodic table, getting into higher atomic numbers, you're going to have energy shells 3, 4, and 5. Each of these energy shells for atoms that are elements, or atoms that are not in the noble gases. In the noble gases, all of their shells are filled correctly, have the maximum number of electrons. And so that's why those noble gases are sometimes referred to as inert, because they are non-reactive. However, and they're non-reactive because all of their outer energy shells, their valence shells, the last energy shell in their structure, are completely filled. They do not have the need or necessity to attract electrons to try and pair up anything. All of the other atoms are looking for additional electrons. So that outer energy shell does not contain all 8 of the electrons that would fill it completely. It may have 7, or it may have 6, it may have 2, but it's looking for additional electrons to fill those shells. So those elements are reactive, whereas we get all the way to the right on the periodic table, those guys are not. Similarities, elements within a column are very similar because they have the same number of electrons in their valence shells. So the way that they bond chemically with other atoms is very similar. Other elements in the same column as nitrogen can also form 3 covalent bonds. So here's our periodic table. You can see here, let's take, for example, nitrogen, right? We looked at nitrogen, so let's stick with that one. Nitrogen has an atomic number of 7. In the same column here is phosphorus, which has an atomic number of 15. So even though they vary in the number of protons, nitrogen has this outer shell that has these 3, right? This outer energy shell, its valence shell, has 3 electrons that are unpaired. Well, phosphorus has the same thing, 2 and 3. So phosphorus can also bond with 3 different atoms, or can share 3 electrons. Let's look over here, carbon. Well, let's go with boron because carbon is an exception. Here we have boron, which forms 1, and then we go down here to aluminum, which forms 1 as well. Then we move over here to oxygen. Oxygen actually likes to form 2. So here we have 2 bonds. And here we have sulfur, which is the same way, forms 2. As we move over, fluorine forms 1. Chlorine forms 1. And then we get to our inert gases here. Neon is a non-reactive gas. That's why they use it to make all of those signs, all the neon signs that we see. That neon gas is part of that process. So this guy has no unpaired electrons. Look at all of its electrons. They're all paired. So this guy does not want to share. Argon is the same way. It's all paired up, so it doesn't want to share. Now, atomic mass is kind of what we might think of as the weight, right? As the weight of an electron, of an atom. So protons and neutrons are almost equal in their mass, and they are about 1,800 times the mass of an electron. So they're much, much larger than electrons. So electrons are pretty crazy little subatomic particles. Atomic mass tells us the mass of, when we look at the atomic mass on the periodic table, right? It's just above the atomic number next to the symbol for the element. That atomic mass is in relation to the mass of other atoms, and the atom that most atomic mass numbers are compared to is going to be carbon. Right? So the most common form of carbon has 6 protons, 6 neutrons. This gives it an atomic mass of exactly 12. Hydrogen has an atomic mass of 1. That means it is 1/12 the mass of a carbon atom. Magnesium has an atomic mass of 12, which is also twice the mass of a carbon atom. So let's take a look at how this works. Is mass or weight the same thing? And mass is, think of mass as size. Weight is how much gravitational pull does the Earth have on that particular mass. So if a man weighs 154 pounds on Earth has a specific gravitational pull and it is consistent. But if he goes and lands on the moon, he's only going to weigh about 25 pounds. But if he lands on a neutron star, which has a gravitational pull that's much greater than Earth, he could weigh up to 21 trillion pounds. However, the size of the man, the actual size or mass, is the same in all 3 locations. Atomic mass is measured in daltons, and molarity is just a concentration. It's Avogadro's number, and it's used in chemistry when they are mixing chemicals, and basically like a concentration. How many atoms of that particular compound, like say hydrochloric acid. What's the molarity of the hydrochloric acid? What we're looking at is how many moles of atoms are in a particular concentration. And so Avogadro's number is that 6.022 times 10 to the 23. So a single mole of any element has 6.022 times 10 to the 23 atoms. So if you have hydrochloric acid has a molarity of 6, you're looking at 6 times 6.022 times 10 to the 23. Isotopes are different forms of elements, and this is because they differ in their number of neutrons. So it changes the atomic mass. Right? So carbon-12 has 6 neutrons, whereas carbon-14 has 8. And this can change because its atomic mass is different. It can change some of the characteristics of that particular element. You may have heard of carbon-14 dating. And so carbon-14, which is a heavier carbon, has a longer half-life and is what is measured when we look at fossils and like ancient artifacts. They may do this carbon-14 dating. They're looking to see how much carbon-14 is still present in that particular item so that they can get an idea of how old it is based on how long it takes carbon-14 to break down. So it's known as carbon dating. Atomic masses in general are usually just an average of all the different atomic masses of all the different isotopes, known isotopes. So if carbon has, say, 7 or 8 different isotopes, so different forms of carbon, all with the same number of electrons and protons, but differ simply by the number of neutrons. See, this isn't changing the charge because protons and electrons are the same. It's simply changing the atomic mass. But changing the atomic mass can change the characteristics of the atom. So they take all these different atomic masses, add them up, divide them by the number of different versions they have, and they come up with an average weight. So let's talk real quick about the big 4. Now, hydrogen, oxygen, carbon, and nitrogen are the 4 elements that are required to make up living things. We are not going to survive without them. We are made up primarily of molecules known as macromolecules, which are carbohydrates, fats and lipids, nucleotides, and proteins. And that's the majority of what our cells and what our bodies are made out of. And all four of those macromolecules require all four of these different elements: hydrogen, oxygen, carbon, and nitrogen. So these four elements make up approximately 95% of the atom, of the 95% of the atoms that are found in living organisms. Hydrogen and oxygen occur in water and in carbohydrates. Carbon occurs in all four of them. I'm sure everyone's heard we are carbon-based organisms. Nitrogen is found in proteins and nucleotides. So all of those big macromolecules are necessary. Mineral elements are very trace, and then we have, of course, trace elements. They're needed for many of our proteins to function and our cells to carry out certain properties and certain functions, but they are needed in very, very, very small numbers. All right, we're going to end here for right now. We will move into chemical bonds and molecules in the next lecture. Just thought you might like a break, and I will see you all soon.